So, hi teacher. I'm going to be presenting this part. Right now, I'm not sure if Alberto is going to have the chance to participate because we've had a really busy week, but he has helped me with the presentation. I'm just doing this individually, just in case that we don't get the chance to coordinate. So here we go. We're going to be talking about the organic pollutants used here. And first off, as an introduction, when we're talking about organic pollutants and the risk assessment, there are three main mechanisms or properties that we have to take into account. First off, we would be talking about the dispersion, also the environmental stability, and finally, we'll be talking about the toxicological and more specifically the eco-toxicological effects. When it comes to organic compounds, and specifically pollutants, they secrete, they transform, they degrade, and they end up building new organics. And this is relevant because this creation of new compounds is a process that has been heavily influenced and altered by the human component, which it's us. So these natural cycles of materials, they are altered in a way that has a severe environmental impact in a negative way. And this in itself is affected by a variety of factors, which would include the industrialization that has been happening since approximately the mid-19th century, also population growth, and hand on hand with this would be the subsequent increase in product and service demands that increase in population requires. So all of these contribute to the synthesis of xenobiotics, which are, I guess you could classify them as man-made artificial compounds. And this means that they're not naturally occurring in the environment. They are foreign to living organisms, and they often include some like drugs, carcinogens, and they're essentially compounds that are introduced into the environment in an artificial way. Now, moving on to the next one. When we're talking about organic pollutant assessment, like I mentioned, we have three main pillars, and first we're going to be focusing on pollutant distribution and dispersion. And in this case, when you have the pollutant environmental relevance assessment, you can make use of certain parameters in order to better understand how these compounds behave. So you have the distribution and accumulation, also, like I mentioned, the ecotoxicological effects and the environmental stability. Now, so when you're trying to identify high-risk compounds, these often leads to the creation of priority pollutant lists. These are, I guess you could call them inventories, in which certain countries and certain pieces of regulation help determine a series of compounds that are considered, like I mentioned, high risk. And as you can see in the table here, we can see that we have the Environmental Protection Agency from the United States in 2014. They identified a proportion of organic pollutants, which is about 88% of. And if we compare this to something from the European Union, like the Water Framework Directive from 2008, we have the exact same proportion of organic pollutants, 88%. And in the Canadian Environmental Protection Act, the very first list that was published in 1989, we have 84%. And as we can see, these are all from different years, and the proportion of organic pollutants has remained constant and has maintained a rather high proportion. So again, this is only to further proof that organic pollutants are a real issue. Also, we have the registration, evaluation, authorization, and restriction of chemicals, which is also an European piece of legislation. And some of the criteria that they include for the chemical evaluation would include persistence, bioaccumulation, and toxicity. Now, when it comes to more specifically the dissemination of organic pollutants in natural systems, we can have two main modes or two main processes, which would be transfer and transport. Now, when you're talking about transport, the most relevant characteristic would be that the movement remains locked in one or within one homogeneous space. And the sequence of events that happens in transport would be that you have a localized emission source. After that, you have the movement of the compounds. And finally, some disappearance processes end up happening after a certain amount of time. And some of the mechanisms that we will be discussing when we're talking about transport would be advection, convection, and diffusion, also retardation, transport via particles, and density separation. Now, the main difference when you're talking about the transfer process would be that the distribution happens between two different phases instead of one homogeneous phase. The two different phases could be water or particulate matter, and that's on a smaller scale. When you're talking about a larger scale, you could be referring to the hydrosphere, the atmosphere, or the pedosphere. And some of the mechanisms that we would be discussing here would be dissolution in water, like deposition, evaporation into the atmosphere, sorption in particles, sediments, or soil. Now, here are some examples of atmosphere and groundwater transportation systems. When it comes to the atmosphere, we have a source of pollution, we have the emission processes, they can happen diffusion, and that transport has convection. It's basically a lot of different processes, but this is mostly talking about the atmosphere. When you're talking about groundwater transportation systems, like I mentioned, you have transport via particles, advection, dispersion, and diffusion, retardation, and degradation. Now, when you're talking about environment transfer processes, as you can see, these are mostly concerned with water resources and aquatic ecosystems, and for the most part, we have dissolution in water, we have sorption on particles, sediments, or soil, evaporation into the atmosphere, and wet deposition, which can be either rain or snow. Now, the grasshopper effect, that one's a bit here. So what you have here in this diagram, we can see it's essentially, it has been called a multi-hopping process. And in this case, persistent organic pollutants manage to be transported over long distances. And it's essentially an evaporation and deposit process that happens repeatedly. And there's certain elements like vapor pressure and global warming which influence the way in which persistent organic pollutants behave. And like I mentioned, there's an evaporation process, and after that, it's followed by a deposit process. And the best way I think I can explain it is that if you have a certain organic pollutant that is maybe originated, that has its emission source in maybe Mexico City, what can happen with the grasshopper effect in this multi-hopping process is that these organic compounds can continuously evaporate and deposit, and they can travel large distances. Now, these pollutants, due to factors like climate change and some weather processes, like I mentioned, they can be released in one part of the world, and through repeated or seasonal processes of evaporation and deposit, they can be transported across very vast distances. This usually happens from south to north, based on what I could read. So again, you can have something happen in North America, or maybe Mexico, or maybe even the equator. And through these processes of evaporation and deposit, they usually end up in the Arctic, which are the colder zones of the planet. Now, global warming is really important here because the volatilization is a property that's also really, really important when you're talking about organic pollutants. And this global warming means that the chemical volatilization process is usually more quick or more efficient, which is not ideal. Now, when we're talking about environmental stability, we also have to mention physical chemical properties. The list that you see here on the left, it's just a mix of both physical and chemical properties. When we're talking about organics, you have density, melting and melting points, physical state, intermolecular interactions, and basically these are just a collection of some of the physical chemical properties that we were able to research. And the two most important ones when it comes to environmental stability, and we're talking about, and more specifically when we're talking about organic pollutants, which be solubility and volatility. In this case, we can make use of Henry's law constant, which has pressure being one of the most important points or most important parameters in order to determine it. We have two modes when you're talking about Henry's law constant, and this is basically a ratio of the concentration in the gaseous phase and the concentration that you have in water. Also, you have the optimal water partition coefficient, which is often abbreviated as KOW. And in this case, you're also talking about a ratio. You're talking about the concentration in one optimal phase and concentration in water. Now, the KOW, which be an estimation of chemical absorption on particles, and KH, which would be Henry's law constant, is mostly concerned with the given concentration rate between the gas and the liquid phase. Now, when you're talking about organic pollutants, you also have to take bioaccumulation. But first, we're going to start with bioconcentration and biomagnification. When we're talking about bioconcentration, you are mostly concerned with aquatic ecosystems, and the pollutant concentration of bio reach a constant proportion. This is the most significant property of bioconcentration. You're talking about reaching a constant proportion. And again, it's basically an enrichment process that happens over time until constant levels are reached, and you can use a parameter called the bioconcentration factor in order to determine that enrichment process. And this concentration factor is heavily determined by the pollutant that we are managing, and also the organisms that are affected by it. The bioconcentration often increases with the lipid content, and therefore, as you go higher up the food chain, it increases. When you're talking about biomagnification, it's also an enrichment process, but this one is more focused in the food chain entropic levels. It's basically a ratio that happens between the concentration levels of a compound and the food and the level of food pollution that you have. And as food or energy is passed higher up through the food chain entropic levels, that concentrate the properties of those compounds tend to increase as well. And when you're talking about organic pollutants, usually what happens is that you have heavy metals in organic compounds that are really harmful. And as they climb higher up the food chain, they end up being even more harmful than they already are. So based on what I could understand, the animals and the organisms that find themselves higher at the top of the food chain are the ones that run the most risk, because a compound can start off in a very small animal, maybe a rabbit, or maybe a mammal that's really medium-sized, small, and as it climbs higher up the food chain, it becomes increasingly harmful. So bioconcentration is more concerned with reaching a constant proportion. It's also concerned with the food chain, but not as much as biomagnification. Biomagnification is concerned with the concentration level and how that relates to the level of food pollution. And like I said, it increases. It refers to the increase of organic pollutants strength, you could say, as you go higher up the food chain. Now, bioaccumulation is essentially sum of both these factors that I was mentioning here, bioconcentration and biomagnification. And bioaccumulation can be defined as a process of accumulation of chemical substance that happens in living organisms. And like I was mentioning, biomagnification and bioconcentration are both processes that can be summarized as bioaccumulation. Now, when you're talking about ecotoxicological effects, you hear there are arguably a really important parameter that helps us assess the impact on the environment of a pollutant, and in this case, organic pollutants. And here, essentially, it's not really, we don't have a lot of information here, but it's ecotoxicology focuses on studying the effects of environmental chemicals in a rather comprehensive way. It takes into consideration a lot of factors. And here, we're also going to be focusing on the impact that chemicals have on organisms. Now, in order to characterize toxicological effects, there are three main aspects that we have to take into account. That's the pathway of exposure that we have. It can be through the skin, through inhalation, through the mouth or nose. Also, another factor or another aspect that we have to consider would be the frequency and the quantity of the uptake of the compounds, and in this case, organic pollutants. And finally, we have temporal lag effect, which is how long that compound is going to be affecting a human being or living organisms. And that would be it. So thank you.